Hello, I'm Bryony Worthington, and this is Cleaning Up. Since we recorded this week's episode, which looks at the huge contribution the American scientific community has made to the safety of our planet, swinging cuts have been announced to the National Oceanic and Atmospheric Administration, and thousands of scientists and citizens have taken to the streets in protest. We hope you enjoy the following two interviews, which serve to illustrate what's at stake as the USA seemingly turns its back on science, with huge consequences for us all.
I mean, it does feel to me that this foundational science that's being done here is essential for us to be able to manage this problem. As you say, it's about knowing whether what we're doing is working. It's about knowing how bad things are getting, how quickly. But are we at a point where we could see US funding being cut from some of these services?
I guess it's important to point out that my father had a challenge throughout his career, which was to keep the measurements going. So it has never been easy to sustain these kind of long-term observations. I mean, the way science sets priorities is it usually looks at how we can do something new, how we can do something that's transformative that hasn't been done before, and repetitive observations of the environment, as critical as they are, don't fit easily in that mix. And so it's been a challenge for him throughout his career to keep the measurements going. It's been a challenge for me to keep them going. And people look at these measurements and say, wow, that's important, that's fundamental, but it's not what we do.
Hello, I'm Bryony Worthington, and this is Cleaning Up. This week, I took a train along the Pacific coast to San Diego, home of the Scripps Oceanographic Institution, perched alongside one of California's most popular surf beaches, and where many brilliant people are helping to understand our complex planet and the rate at which it's changing. My first guest is Professor Ralph Keeling. He has carried on the work of his late father, Dave Keeling, who first started systematically measuring global concentrations of carbon dioxide in the atmosphere, giving birth to the famous Keeling Curve. Ralph's own career has included a focus on the much harder job of measuring oxygen levels, not because they're in danger of running out, but because it helps in understanding how much of the excess carbon dioxide we release is being taken up by land and how much by the ocean. We covered a range of topics, and I was struck by how important empirical measurements really are for alerting us to what's going on in the world. Carbon dioxide concentrations are still rising, and the rate at which they're rising is also rising. But as Ralph explains, when we kick the fossil fuel habit, we should see this trend turn around relatively quickly. So for lots of reasons, it would be a huge loss to humanity if these services were for any reason to be interrupted. My second guest, Professor Ray Weiss, is a geochemist and atmospheric detective. He focuses his attention on other gases, which are destroyers of the ozone layer and in some cases also agents of climate change. But please first join me in welcoming Professor Ralph Keeling to Cleaning Up.
So, Ralph, it's so lovely to be here with you at Scripps Oceanographic Institute. We're going to kick off with the first question, which is always to introduce yourself using your own words, please.
Okay, yeah, so thank you and welcome. I'm Ralph Keeling. I'm a professor at the Scripps Institution of Oceanography at UC San Diego. I've been here for a few decades, and my father before me was here, so there's a family tradition. And I work on carbon dioxide in the air and on oxygen in the air and in relation to climate change.
Your surname, which is obviously a very famous surname, the Keeling Curve is named after it, which was really your father's invention. Could you tell us a little bit about how that came about? How did the Keeling Curve come to be?
Right. So he started measuring carbon dioxide in air while he was at the California Institute of Technology as a postdoc. And it came about because he was there, he wanted to do something outdoors. There was no particular topic queued up for him to work on, and he embraced a project to study carbon in river water. There are not too many rivers in Los Angeles or nearby, so he got to go driving up the coast to a place called Big Sur, lovely spot, camping and looking at the composition of river water. He realized quite quickly that he wasn't going to figure that question out, what controlled carbon in rivers, unless he knew what was in the air. So he developed apparatus and methods for measuring carbon dioxide in air. It was very playful work. And he started noticing there was more regularity in the CO2 in the atmosphere than anyone had noted before. He was noticing he was almost always getting about the same number in the afternoon. He would get higher numbers at night, but it was somehow coming back to the same number. And he looked in the literature, and the previous literature suggested carbon dioxide varied widely in the atmosphere. So he realized he was onto something.
And what was this era? So was this in the 1950s?
This was the mid-1950s.
50s, right.
Right? So
climate really wasn't an issue. Like CO2 and greenhouse gases weren't really being talked about at that point?
Hardly at all.
Yeah.
But it was beginning to be talked up because there was work done that was disputing some of the... Originally there was a body of work published by Svante Arrhenius suggesting carbon dioxide could affect climate. Then that was kind of viewed skeptically. And in the 50s, there was a guy named Gilbert Ploss that did calculations again of absorption of heat radiation or thermal infrared by carbon dioxide, and showed that, yeah, indeed, it probably would be causing an effect. And but what hadn't been addressed was whether carbon dioxide actually was building up in the atmosphere.
And how you could tell it.
And how you could tell.
Yeah. Because one of the features of it is as you know, as the biosphere exhales and inhales, it does fluctuate, right? So was the challenge, how do we find a constant measurement that we can be confident in?
Well, I think the issue was that people thought that carbon dioxide was highly variable. So in order to track a trend, you would have to do extensive sampling of the atmosphere to average over and get some kind of statistical average. My father was equipped with two things that really put him in the center of the conversation. And the first was he realized that the atmosphere might not be so variable if you went to a clean enough location where you didn't have a forest nearby breathing in and out carbon dioxide. He saw that because he could see it already in the afternoon measurements. What's special about the afternoon is that the sun is heating the ground and the atmosphere is churning up. And so you're basically getting an air sample that's reflecting a deep column of air connected with a larger hole. So he was seeing kind of a core property of the atmosphere that hadn't been noticed before. So that's the first thing he had. The second thing he had was he had new methods that were better than anyone had before for measuring carbon dioxide. He became the person who was basically most qualified to run a program to see if you could detect the buildup of carbon dioxide. And among the things that happened in that early program was measurements at Mauna Loa, the big volcano on the big island of Hawaii.
Yeah.
And that became eventually the Keeling Curve. It's this amazing record showing the buildup over time.
Yeah. And the sawtoothed nature of the curve, did that cause, I mean, did your father kind of predict that would be the case, or what? I mean, it must have been quite, watching these readings, he was really on the frontier, wasn't he?
Yeah, it's actually a fun story because when they put the instrument out on Hawaii, it initially delivered almost the exact number that my father expected. Remember, he said there was a background value and it was giving him about 310 parts per million. That's perfect. Confirmation. Now all we have to do is track it over time and we'll see the buildup. Except that it was trending downwards.
Turns on this machine.
No. Actually, it was flat. I get it right. It was flat, and then there was a power outage, and so like a month there was no data, and then finally they get the instrument back on again, and it's now at a lower level, and it's drifting downwards. And then there's another power outage, and it's starting off even lower, but now it's drifting upwards, and so he didn't know whether he had a bad instrument. Right at that point, he was troubleshooting. And it was but he couldn't figure out what was wrong with it. So he kept it going, and then it goes up, and then it was on for a while, and then it starts down again. And about the beginning of the second year, he looked at this pattern and said, "Oh, it's doing what it did last year. This is a seasonal pattern."
Right.
And at that point, there was a big aha. Well, how surprising is that? Because trees grow in the summertime and they're taking CO2 out of the atmosphere, and that's mixing throughout the northern hemisphere. Although the forests are far from Hawaii, the air is circulating. So he's seeing the breathing of the planet showing up. So he saw that before he saw the buildup. But then a couple of years later, he could see it was already at a higher level than the year before. There was still going up and down, but from a higher base. Yeah.
And that sort of those sets of instruments that were put in place there in Mauna Loa in the 50s are still being operated today? Bring us right up to date in terms of
the instrument he put out there it might have been swapped for a replacement of identical sort, but the same design of apparatus was kept going there until really about the time that my father passed in 2005, and I took over, and I was realizing, okay, well, there's something to sticking to the same thing for a long time, but at some point you have to modernize.
Right, okay.
I mean, it was producing brilliant data, and
Yeah.
the main limitation was the amount of work you had to do to maintain it.
Right.
It was like a fussy old, imagine trying to keep an old car running,
Yeah.
right? It's expensive after a while.
So
And so we modernized it, but it's the same principle. It's an infrared analyzer. It measures absorption of infrared light in particular wavelengths that allow you to detect and quantify carbon dioxide. And then it uses a calibration scheme where you send reference gases, that's really air and compressed air cylinders, where you know the amount, and then you can calibrate it. And a lot of his early work went into actually establishing calibration methods. Because you put an instrument out there and you get a number out, and okay, it's varying and it's interesting, but how do you know it's right?
Yeah. I had some experiences working on air quality measurements in London, where the number of variables that could alter it, weather and temperatures and.
Yeah, it's not like you just put the instrument out there and get numbers and then worry about calibration. Calibration had to be really carefully worked out as part of the program. And by the way, he had a new approach to doing calibration as well. And in fact, the early work he did at Caltech was using a method not using an infrared analyzer. And so when he was measuring river water and the air above it and so forth, the way he was measuring carbon dioxide was a very simple method that involved taking an air sample. First of all, you capture a volume of air, you know how many molecules you have because you know the pressure, volume, temperature. So he knows the amount of air, and then he would pass the air over a trap that would freeze out the carbon dioxide. And that was possible because you can freeze out carbon dioxide very efficiently at the temperature of liquid nitrogen, which is like this white bubbly liquid that people have seen in the lab. And liquid nitrogen had just become available as a readily supplied commercial product. So he was taking advantage of the latest technology, liquid nitrogen.
Liquid nitrogen.
And that method had the merit of being really absolute method. You just number of molecules of CO2, number of molecules of air, the ratio is this parts per million.
It's a volcano. That's one question I had. Was, how stable is the Mauna Loa location? Have you had issues where, it's a fairly active part of the world? So, yeah.
Well, in late 2022, as some people may remember, Mauna Loa, after being dormant for many decades, started erupting. There was a sense it was happening because there were little, rumblings and things. But yeah, sure enough, there we go. And the station is pretty remote. It's a huge mountain, not in the sense of being sharp and tall, but it's just a massive lava dome. But most of the upper slopes of that have been buried under lava flows repeatedly. That's why there's a mountain there at all. And not very old, just maybe 100 years or less old. And the road cuts across lava flow after lava flow. And so you just knew that at some point there was going to be another lava flow that would cut the road. And that's what happened. So this lava flow did not impact the observatory, which was further up, but it did spew a whole bunch of lava right across the road. It also, the power lines to get to the station ran along the road. So they were out, the road was out, and neither is back in yet. So even after this time, the only reason the station is operating is because it has been accessed by helicopter and there was solar panels installed. I should say that the observatory where these measurements were made, the Mauna Loa Observatory, was also something that was newly established at the time my father started these measurements. He didn't set up the observatory. That was set up by someone else in the Weather Bureau called Harry Wexler. So it's a NOAA observatory that collaborates with us to get these measurements. By the way, they have their own program for measuring carbon dioxide. So they have a big program. So there's an overlapping set of activities going there with us and NOAA.
Yeah. Which is it is a big contribution from the US to the world, really, right? That this station has become globally famous for this data. It's telling a very compelling story. It's something that the US can, I think, feel great pride that this is something that was done, right?
That's right. I mean, Mauna Loa is now one of many stations, but it's kind of it's the flagship. And there's a good reason for it, because it's, as I said, my father wanted to get away from influences to measure the background air, a big piece of the atmosphere. What better place than on a volcano sticking up in the middle of the ocean with no big land masses anywhere nearby? So you could say it's like probing your core temperature in your body, right? You can get a holistic measure of health by measuring some core property.
So where are we today? So obviously we've detected the concentrations are rising.
Yeah.
What's the rate at which it's rising? How worried are you about the sort of current? Where are we in terms of parts per million?
We're up there. I mean, we're at around 425 parts per million. It was around 310 or so when my father started. We do know now that before the Industrial Revolution, for a long period of thousands of years, it was around 280 parts per million. So it had already gone up a bit by the time my father started, but of course, much, much more since then. And it's very worrisome, not just because it's up there high. I mean, it's at a level where it's having profound impacts already on climate, on our livelihoods, and all sorts of things that we depend on. But it's also going up faster than ever. And
so the rate of so we're adding roughly 2.5 to 3 per year, are we, parts per million?
Yeah.
Yeah, but that's slightly inclining. So we're heading into a steeper curve at the moment?
If you look decade by decade, it's constantly going up faster. If you look year by year, not so clear, because some years have little temporary spurts and other years slow down a little bit. But yeah, the overall course of it is accelerating. We understand that. I mean, it's accelerating upwards because the combustion of fossil fuel has continued to grow. So every decade we burn more fossil fuel, we add more carbon dioxide waste, pollution into our atmosphere, and it builds up. And so the more you add, the more it builds up. So there you have it.
Yeah, because the long-lived nature of the gas means, it's not cycling out the atmosphere unless it's being absorbed by the biosphere.
It is somewhat being absorbed, but it fundamentally is a cumulative problem. What I mean by that is it's a little bit like just dumping waste in a landfill. You put it there, and it's still there. Now, this is a case where the extra CO2 we put in the atmosphere might spread into the ocean, or it might be taken up by plants, but there's still extra carbon out there, right? So it's carbon that was in the ground that's now somewhere else, and the atmosphere tends to take up sort of a fixed fraction of that, so it's still building up cumulatively.
And just thinking about that biospheric sink, roughly half of the greenhouse gas emissions that we're tracking, it seems, are being absorbed by natural processes.
Yeah, we're considerably better off than we would be, because we have these natural sinks that have taken up some of the carbon dioxide, and roughly 50% of what we've emitted has gone elsewhere. And there's not too many possibilities.
Yeah, it's got to be plants or the ocean, really. But what happens? Are you at all seeing any sign that the biospheric sink could be weakening?
There's we don't understand fully exactly what's controlling those sinks. The situation is a little, so there's some of it's going into the ocean and some of it's going into the land. And maybe I should pause here and say that when I started my career, I was very inspired by my father's work. I was trying to figure out what to do, and what he looked really important and exciting. And he mentioned to me that one of the things that he had meant to do, not because he was trying to coach me in a career path, he just mentioned this, that one of the things he always meant to do was measure the corresponding changes in atmospheric oxygen.
Right.
Because these fossil fuel burning, you're taking carbon, you're combusting it, releasing CO2. Well, guess what? Combustion takes up oxygen, and that came out of the air. So there should be less oxygen while there's more CO2.
Right.
And the reason for wanting to measure oxygen was mainly because it could help you dissect this question of whether the carbon dioxide that wasn't in the air was mostly going into the oceans or into the land.
Right.
The difference being that when the land takes up carbon dioxide, it does it by photosynthesis, which produces oxygen. So there's a buffering effect, not just on the buildup of CO2, but also on the loss of oxygen. Whereas if this carbon dioxide is taken up by the ocean, that's an inorganic chemistry. There's no buffering on oxygen. So oxygen gives you a really nice handle on that split. And so we were able to show that, it is about 50-50 going into both. But you asked the question of, whether there's potential for these sinks to weaken in some way in the future. And I think in the case of the sink on land, which is somehow tied to photosynthesis, there's certainly potential, because the processes responsible for that are not super well understood. There's a series of processes that may be possible and almost are certainly contributing, and there are models that can account for what's happened reasonably well. So there's a framework for addressing this, but it's not super robust. Whereas in the case of the oceans, the main process that's going on in the ocean are well understood. It's simple. CO2 dissolves in the water. It reacts with the other ions in the water, which is a buffering reaction that helps the ocean take up more. But it wouldn't continue to take up carbon dioxide, except that the water at the surface, which would saturate, then is mixed with water below. And so you can have a continued uptake because there's a large body of the ocean that hasn't seen the atmosphere.
And it's got its own natural circulation, both at sort of continental scale and at, I presume, at a regional scale, which means it's churning. And
right, the oceans are constantly churning, so you need to know the churning rate, and you need to know a little bit about chemistry. That's the main control on ocean uptake.
Right.
Now, the biology in the ocean also plays a role.
Yes.
But it's not the main thing.
Yeah, but on land, it's a little bit more
on land, it's all biology, basically.
Yeah,
it's all biology.
Biology is hard.
Biology is hard. That's the point.
That's the point. And this kind of, and also, I guess, when I was starting out thinking about climate change, maybe, I don't know, 25 years ago, I was worried about sea level rise and storms and, extreme weather, but I didn't have on my list most of the temporal forests are on fire in my lifetime, and I wonder, now that you've been able to do that sectioning off of the land and the ocean, how worried should we be about loss of some of this big, the forestry sinks, for example?
I think we should be worried because, trees are just sitting there, and it's not a very permanent reservoir. All trees die, of course. So here's an important point about a forest. Trees don't scrub carbon from the air. They're not a cleanser. They take carbon out of the air because they're building biomass. So the only way we can solve the climate problem by having forests is if we increase year by year by year by year the amount of biomass. It's like trash in a landfill. The extra CO2 has to be somewhere. If it's not in the air, it has to be either in the oceans or in biomass. And so if we're building up carbon in some reservoir that's there right out in the climate system or easily disrupted or burnt, then it's not a very permanent storage. I mean, the carbon was deep in the ground for millions of years, and now it's out there.
Yeah, and there's been quite a lot of discussion, I think, about, how fungible, how exchangeable are these ideas. There was this period when everyone got very excited about planting 1 trillion trees, and that's suddenly the answer. But, clearly that's not a like-for-like swap. As you say, you're taking something that was stored for millennia in the lithosphere, putting something into a fairly temporary kind of storage system, which we don't properly really understand. Is that fair?
That's fair to say that. No, you put it very well. Yeah, it's not like for like.
Yeah.
Exactly not. And but there are some things that are more permanent, like the dissolution in the ocean is more permanent. And some of the planned interventions for carbon capture, to the extent they involve putting carbon dioxide in a deep geologic reservoir, that would be, again, it's kind of, you want to get the carbon deep away from the atmosphere, something that doesn't make rapid contact with the atmosphere. And a forest isn't that.
Right. Yeah.
But there are some, and also, one of the solutions that's talked about is modifying seawater chemistry to have it take up more carbon. And that actually is in the category of something more permanent, because the modification actually involves taking minerals out of the ground.
Right.
So it's another long-term intervention that has a certain kind of permanence.
Yeah.
Doesn't mean it's a good idea.
And I'm really interested by this oxygen measurement. Like, I haven't really heard about this, before researching, learning about your work. So tell me how hard that was, and it's. But I've got two questions. One is my niece wrote me a lovely handwritten letter when she was learning about climate change, very worried that we were going to run out of oxygen. And I confidently said, no, don't worry. but I didn't really know. And so tell me about this process of measuring oxygen.
Well, I'm probably the only person in the world whose life would be easier if we were about to run out of oxygen, because it would help justify what I do.
Right.
But we're not.
We're not. Okay, good. The good news is, right?
The good news is we're not.
Yeah.
But it's still really important to measure because it has diagnostic value.
Right, because it's going to help us understand this.
Yeah, it's a super important diagnostic value. I mean, one way to look at it is you could say, what do we know best? What's the one number that really counts? Well, it's how much CO2 is in the air. and how it's trending over time. That we know that better about the carbon buildup than anything else. We know that better than we know the amount of fossil fuel we burn. We know that better than individual sinks. What's the next best number we know right now? It's how fast we're losing oxygen.
Right.
So we really, and that's another cap on the combination of processes that are coming into play, and it particularly, as I said, helps you split land and ocean sinks, and that's really important. So, for example, if we had a sudden turnaround where the land started emitting carbon, how would we know whether that was the land messing up or the ocean messing up? Okay,
Right.
so we would nail it. Or let's suppose we intervened with this sort of alkalinity enhancement and allowed the ocean to take up more carbon. We would see that, but you might see a trend in CO2 that's different, but you wouldn't know whether it was the land or the ocean. So you didn't verify that what you did made the difference.
Yeah, and how easy is it to measure oxygen? Is it like CO2 in that it's well spread and you can sort of tell me about this process. Was it a hard process?
Yes.
that one word answer probably covers a lot of stories.
Yeah, it was many years going into trying to figure out how to measure it well enough to be relevant. And why is it hard? Simple. It's the same reason it's not an environmental concern that we're losing it. There's so much of it.
Right. Okay.
So we're trying to kind of looking at little drops in the ocean, right? We're living in an ocean of oxygen in the atmosphere, and as much as we're reducing the amount, it's pretty small, and so we have to measure really, really carefully to see this tiny change. So carbon dioxide is a trace gas.
Yeah.
Right, 425 parts per million today, say. Oxygen is around 21%.
Wow.
So it's a big fraction. People know that, right?
Yeah.
We live in an oxygenated atmosphere.
We wouldn't be here if we didn't have that, yeah.
And so we're just really marginal changes in it. So it required developing instrumentation that measured the abundance of gases, oxygen and air, to a higher level than anyone had worked out before. So it was a fundamental measurement challenge, which actually appealed to me. I liked working on something that was the better widget, how to make a better widget.
Yeah.
But the difficulties didn't stop there, because the other thing that makes it hard is that air comes apart if you're not careful with it.
Right.
To a small degree.
Yeah.
So you think of air as just a mixture of oxygen and nitrogen and argon and CO2, and it's just this one number. But one you could quantify how much of each and get what you wanted. Take a sample and measure it. But the problem is that if you have differences in temperature between one side of your sample and the other, it turns out the oxygen is going to concentrate on the cold side and the nitrogen is going to concentrate on the warm side. And when you take a sample, you can preferentially take in more nitrogen than oxygen if you're not careful. In other words, you can interfere with what you're trying to measure as you're trying to do it, just by how you're handling the gas.
Goodness. So
we have to be we had to work out different, we had a better measurement method, and then we had to work out, a better analyzer. And then we had to work out techniques for handling samples that was different.
How does the Scripps Institution feel about its role in this moment in history where we're as you said, the parts per million are rising fast? It's kind of a moment in history where climate denial unfortunately is coming back up the agenda, and yet here we have this very, very obvious data.
Well, I guess I would say that the challenge to the notion that the carbon dioxide buildup is real and that it's caused by humans, there hasn't been much of a challenge to that. And that's because that's the sort of the power of my father's achievement in the continuing measurements, is that they're kind of unassailable. It's so clear it's building up, and it's so clear it's because of human activity. Even some of the most notable skeptics didn't try to take that one on. It was just and for the same reason, it's a good starting point for trying to understand what's going on, because this is something you don't have to get deep into the weeds to appreciate its importance.
What would it take for us to actively start to see it either plateauing or starting to come down? We talk a lot about temperature targets, but they seem they're an order away from, they're like a derivative away from the parts per million.
Well, the main control knob is how much fossil fuel we burn. It's that simple. So if we did not keep increasing our use of fossil fuel year by year, but burnt the same amount every year, which, by the way, is not a good target for stabilization, what would happen is that CO2 would continue upward, but it wouldn't accelerate upwards. So the first milestone would be to see that it's no longer accelerating. But of course, it's still going up. So climate is we're still moving into uncharted climate territory. So that's very scary. So what you really need to do is get to a point where you stabilize temperatures. And based on significant body of evidence, the best place to the way to do that is to get our emissions all the way down to zero. But in terms of milestones in the curve, we could see it no longer rising. We could see it starting to rise more slowly. We could see it plateauing. We could see it starting to fall, right? Those would all be different milestones which could call out.
Yeah.
And we haven't even seen the first of them yet.
And how quickly would it respond? I mean, like if we did stop at least accelerating the emissions, I mean, global emissions, they are still rising, but they're not perhaps, I mean, I think there is a scenario where thanks to electrification, we're starting to burn less oil. Thanks to moving into renewables, we're burning less natural gas and coal. We probably haven't got time to go into the sort of geopolitics of all of this because it is different countries doing different things right now. But there are technologies coming into markets now which are cheaper than the alternatives. So, but how long would it take for us to sort of see that deceleration? If we say next year we reach this peak that we're all looking for, how long would it take for the parts per million to respond?
Very, very quickly, actually. I mean, for example, if we completely stop burning fossil fuel right now, just net zero, tomorrow,
Yeah.
carbon dioxide levels will start falling tomorrow, basically. And that's because the buildup, why is it building up? It's because we're emitting every year, but there are also these sinks that are acting to take some of it out. The sinks are a response to what's in the air. There's an excess in the air. So as long as there's an excess in the air, the sinks will still keep trying to take some of that up. So if we stopped right away, the sinks still act, but there's nothing making it up. So it's only being taken out of the atmosphere. There's no lag. That would happen very quickly.
Okay.
It might take a little time for us to detect a change because there's a little bit of natural fluctuation. So you'd have to look beyond that. But so it would probably take months or more to really see it for sure. But it's fast. I mean, that doesn't mean that what's slow is that we can't go to net zero tomorrow.
No,
right?
absolutely.
So the pace will be set by how fast we can convert to renewable and non-fossil energy sources.
Do we need to buy ourselves time? There's an increasing conversation now about could we artificially cool the planet for a decade in order to give us the time that we've lost? We're starting late. We've not acted fast enough.
Yeah, I'm not a big fan of those approaches for a variety of reasons, but it's worth pointing out that even the most ambitious, there's really two kinds of interventions. There's trying to intervene on the carbon cycle, so you're pulling CO2 out of the air or something like that, or you intervene directly in the climate system. And the interventions to try to take CO2 out of the air are going to be expensive. They're going to be slow to spin up. And almost by any reasonable assessment, it's much easier to reduce consumption of fossil fuel with renewables than it is to carry those things out. That said, if you want to go all the way to net zero, you might have trouble getting the last 20%. And so at that point, there's room for these carbon capture technologies to bring us all the way to net zero. And by the way, net zero is not going back to the pre-industrial natural climate. Net zero is the point where we're no longer making the system worse. When we're no longer moving further. That's just stabilization at wherever we got.
Yeah.
Now the other kind of intervention is, as I said, is like doing something with directly intervening in the climate system. Some of those could be quicker, but they're fraught for other reasons.
And they're fraught because it's complicated. I'm not the best person to answer this question, but to me it would feel like how are the countries of the world going to decide that it's okay
to deliberately intervene at that scale in the climate system. I can't imagine there really being an agreement about that.
Cleaning Up is brought to you by the members of our leadership circle. That's Actis, Alcazar Energy, Davidson Kempner, Ecopragma Capital, EDP of Portugal, Euroelectric, the Gilardini Foundation, KKR, National Grid, Octopus Energy, Quadrature Climate Foundation, STCL, and Wärtsilä. For more information on the Leadership Circle, please visit cleaningup.live. That's cleaningup.live. If you're enjoying Cleaning Up, please make sure that you subscribe on YouTube or your favorite podcast platform and leave us a review. That really helps other people to find us. Please recommend Cleaning Up to your friends and colleagues and sign up for our free newsletter at cleaninguppod.substack.com. That's cleaninguppod.substack.com.
I mean, it does feel to me that this foundational science that's being done here is essential for us to be able to manage this problem. As you say, it's about knowing whether what we're doing is working. It's about knowing how bad things are getting, how quickly. But are we at a point where we could see US funding being cut from some of these services?
I guess it's important to point out that my father had a challenge throughout his career, which was to keep the measurements going. So it has never been easy to sustain these kind of long-term observations. I mean, the way science sets priorities is it usually looks at how we can do something new, how we can do something that's transformative that hasn't been done before, and repetitive observations of the environment, as critical as they are, don't fit easily in that mix. And so it's been a challenge for him throughout his career to keep the measurements going. It's been a challenge for me to keep them going. And people look at these measurements and say, wow, that's important, that's fundamental, but it's not what we do.
Right. And is there a risk, because obviously science moves forward through publications, and publications is the currency of an academic institution, and you're not going to get high-ranking publications from saying the same thing you said last year and the year before and the year before, that there's no novelty in it. Is that a problem?
You might think it would be, but actually it's not so much, and it's sadly because things are changing year by year.
Getting worse.
Yeah, there's new stories in it, and as you have longer records, you can see things and make discoveries. So it's these records, because they're long, are the place to look for new discoveries.
Right.
So often you can see something happening first, the rumble. Where do you hear the first rumble of something new? Well, I don't know, something that has a baseline, right? So there is, as much as that is in principle a problem, it hasn't. So they need to get papers out, but there's a burden. It's the overhead of struggling to keep the measurements going. That's the real problem.
And it hasn't ever really been. I mean, you'd think that something like the World Meteorological Organization or another body that kind of, the planet Earth needs a kind of a dashboard, doesn't it? Like, don't we need to know what's going on? And if we have a sort of multilateral process, it's in everyone's interest that we have these instruments blinking away, telling us what's happening. But they're not funded that way, are they? They're not funded centrally.
They're usually not. And yeah, the WMO and other organizations can weigh in and say these things are important, but they don't fund science. So you have to get individual countries and programs to come on board, and then everyone is splitting up and trying to do different things. And it hasn't been a complete failure. I mean, the work has been recognized to be important enough that we have kept it going, but it always feels like we're a few years away from shutting down. And certainly with the change in administration in the U.S., it feels like we could be even under more threat going forward. And I guess, if you go back to the 19th century, science was funded by philanthropy, more or less. We didn't have bodies. And it feels to me like this is an area where philanthropy should play a bigger role. There should be willing to, but it's a different kind of philanthropy than this
Well, I would have thought it'd be quite an attractive form of philanthropy. I mean, I spent some time in philanthropy, and in fact, while we were there, we did fund some atmospheric measurements. We funded some tall tower networks to check whether certain types of biosphere were absorbing as we thought they would. And we did spend a lot of time talking to WMO about what could we do to do something bigger. Because like a sort of, you could imagine somebody like the Bezos Earth Fund saying, right, we're gonna instrument the planet. This is, we're gonna make sure that we've got the right tools to track what's happening. They've certainly got something similar in terms of the level of resources that are available.
I mean, I agree, and I think it should be recognized as important. But it's something that everybody needs, that needs curation. It's not spearheading something that's going to go viral and change the world. So, I mean, it could induce people to think about things in a way that might do that. But the basic activity is curating. So it's the kind of philanthropy that people used to, give to museums and organizations that kept care of, heritage of this or that. So we need to get that back on board and move it over to the environment, and people to see that everyone depends on this. It's really fundamental.
Yeah. And maybe, I mean, here we are at the Scripps Institution. That's named after a family, isn't it? There was the journalists, were they? Or I think they were media owners, weren't they? So you could have the Keeling Curve Institution, or it could be renamed, couldn't it? Because you want your father's legacy to continue.
Absolutely.
But if that requires a little bit of rebranding, then so be it, I guess.
No, that's fine. Maybe I can mention that I've recently launched a foundation called the Keeling Curve Foundation, with the very purpose of calling out the importance of long-term observations of the environment, recognizing that my father was really the archetype for showing how important that was, as well as his life story illustrating the challenges of it.
Yeah, and your life story with the oxygen, so it's a really great continuation. Well, Ralph, thank you so much for welcoming me to your office here.
Okay.
And I don't want to keep you from the surf, because I know...
I'm not sure it's in the cards today, but yeah, thank you.
Okay.
Thank you for thinking of that.
Thank you. Well, it's been a real pleasure.
Yeah, likewise. Thank you.
So that was Ralph Keeling, professor at UC San Diego and president of the Keeling Curve Foundation. While visiting Scripps, I also had the opportunity to sit down with Professor Ray Weiss, who has had first-hand experience in the importance of scientific measurements in saving the world the first time around, when we discovered a rapidly growing hole in the ozone layer. Ray now helps run the Advanced Global Atmospheric Gases Experiment, which is essential in monitoring and enforcing the 1987 Montreal Protocol, the internationally agreed legislation to phase out harmful chemicals which were destroying the ozone layer. Please join me in welcoming Professor Ray Weiss to Cleaning Up.
Ray, thank you so much for sitting down with me here at the Scripps Institution of Oceanography. And your particular branch of atmospheric chemistry looks at all the gases, all the trace gases that are not greenhouse gases. Is that right?
Well, we look at trace gases that are not greenhouse gases, and most of them are greenhouse gases. In other words, practically everything we put into the atmosphere absorbs light in one way or another, so everything is a greenhouse gas. It's a question of how intense the effect is. And many compounds, like the CFCs, are both potent greenhouse gases and depleters of the stratospheric ozone layer.
And I learned just from talking to you, actually, in preparing for this, that we know about nitrous oxide as a greenhouse gas, or certainly I have come across it in that context. But for you, nitrous oxide is also an ozone depleting.
Exactly, it's both. And in fact, it's the natural modulator of the ozone layer. Nitrous oxide is both man-made and natural. It's man-made as a result of enhancing the nitrogen cycle by making nitrogen fertilizer that the microbes then turn partly into nitrous oxide. And that's probably the main reason that the atmospheric values are going up. But we need some nitrous oxide, because otherwise the ozone in the stratosphere would not be modulated as well, and we wouldn't get the right balance of sunlight to the Earth.
It would just keep increasing in its thickness, or potentially.
Well, it would have a steady state value that was different from its natural steady state.
Right. And so we're going to come on to ozone and the work that you did in relation to the hole. But what I found curious about this, the nitrous oxide, of course, is a byproduct of us having more productive land, right? That we're feeding more people, but which arguably has lifted people out of poverty. But it's yet another example of where we've kind of tipped a natural balance into a state that it's not used to being in, and we don't really know the consequences.
I think that's fair to say, and we haven't been even though we're aware that nitrous oxide is important for both of those problems. If you look at the record of its emissions over time, it just keeps going up.
And that's because, unlike CO2, where we've spent decades now perfecting alternatives to fossil fuels, we haven't really started on the replacing of fertilizers, have we?
Well, yes, I think we've become aware that we often over-fertilize, and that could help.
Right.
If we use less nitrogen fertilizer, but I believe without the nitrogen fertilizer that we do make, many people wouldn't have enough to eat.
Yeah. So it's a really wicked problem.
Yep.
Okay, well, let's not get too depressed, because I want to talk to you about a success story mainly, which is the story of the Montreal Protocol and how the world did come together to sort of stop ourselves from the brink of a catastrophe when we decided to phase out the ozone depleting gases. And I'd love to hear your version of that story.
It's not easy to give you a short version, but I would say the sequence of events come from three people, none of them still alive, by the way. Paul Crutzen, who also taught here and in Germany, was an atmospheric chemist, was a very creative man. I knew him moderately well. And he figured out that the mechanism by which nitrous oxide modulates the ozone layer. And it's through odd nitrogen compounds that react in the stratosphere in the presence of ultraviolet light. And they play a controlling role in how much ozone there is in the stratosphere. You don't want too much or too little. Because he did that, other colleagues, namely Mario Molina and Sherry Rowland at the University of California, Irvine, figured out that you could have similar chemistry with the chlorine that is released into the atmosphere by the disassociation of CFCs by ultraviolet light. And again, the ultraviolet light doesn't do that in the lower atmosphere because the ozone absorbs the ultraviolet light. But as soon as the gases diffuse upward into the atmosphere and get into the area where there is ultraviolet, you can produce these chlorine atoms. And the chlorine atoms turn out to be very effective at destroying ozone, and they figured that out.
And these CFCs were being used in industrial processes, but they were increasingly being applied into all sorts of uses. And what I recall about the ozone crisis was that there was a quite easy to detect smoking gun, right? That the data that we were able to gather was pretty compelling.
Well, the first measurements were actually made by people at the UK at Halley Bay Station in Antarctica. And actually the Antarctic ozone hole had been there in the NASA data, but their original algorithms filtered it out. They thought it was a mistake.
Wow. So we've got this data-informed, chemistry-informed crisis that the world wakes up to, but we managed to come together as humanity and form the Montreal Protocol.
Yes.
But then there was the question of how is that going to be enforced, or how are we going to know?
It had to be accepted, of course.
Yes, I've skipped over that bit.
And that was the big problem.
Yeah.
I was just a young guy when all of that was, I was a junior PhD level scientist, but the giants of these discoveries, I think particularly Sherry Rowland at University of California, Irvine, he picked up the political cudgel. And worked on it. And it was really the discovery of the Antarctic ozone hole that began to persuade people that there was a more general issue with all of the ozone in the stratosphere that had to do with this. And I think that this is actually a good example of the chemical industry putting some sharp minds to bear on this. There was a time when people were saying, oh, we couldn't have electronics because we didn't have CFCs for cleaning things. And we couldn't have, it wasn't just about hairsprays. There were all these dire predictions that we would be in trouble. We wouldn't have refrigerators. And it was the chemical engineers at the big companies that came up with the alternate compounds, which I think really made it work.
If only one country's engineers had solved the problem, it wouldn't have been an outcome that we could celebrate, right? Because even if America had phased it out, if China hadn't or India hadn't, that's why we needed the Montreal Protocol, right?
Yes, I think that's partly true, but it's also true that these companies are all international. And if somebody develops something, whether it's in China or the US or somewhere in Europe, if it's going to make money, it's going to make money.
Yes, but I'm just trying to think about why we haven't had such a breakthrough on climate. It's a completely different issue, but it must also be...
Because there are fewer alternate solutions.
Well, is that true, though?
Of scale, yes.
Of scale now,
yes.
but if 40 years ago...
Because we use so much energy, and we are so dependent on fossil fuels. And, the greatest hope, I think, was from nuclear energy. And I think we probably blew that one. We didn't do it as well as we should. People have, because of nuclear weapons, you know more about this than I do to some extent, but because of nuclear weapons, people are afraid of this energy source falling into the wrong hands.
Let's go to the Montreal Protocol. The substitutability makes it possible. We start to see dates set for the phasing out, and they're phased out over different timescales for developing countries versus developed, and it's all sort of worked out. But then the question is, well, how do we know if we're winning? Like we need to be able to sort of police this agreement in some way, and that's when you got involved.
That's when I got involved. In fact, a lot of credit belongs with my colleague Ron Prinn, who's a professor at MIT, and he began to think just after these discoveries were made, really in the 1970s, he began to question whether the countries of the world, as we started to formulate the Montreal Protocol and the ozone layer, knowledge became deeper and more severe. Ron began to think about whether the countries were actually going to do what they said they were going to do. And he thought, well, we'll start this problem with a global survey.
And by survey, you don't mean filling in a paper form.
No,
you mean
I mean a survey of measuring the global atmosphere.
Yeah.
So the idea was to put some stations in clean air places so that you would really measure the background, and you wouldn't want to measure the global trend in the middle of New York or London or someplace like that. You'd want to measure it on an island in the middle of the ocean, etc. So Ron, working with colleagues in the UK and Australia and in the US, set up a group of 5 stations to monitor these things in the atmosphere. And the beginning answer was that that was a success, that the rates of increase were decreasing, and eventually the amounts were decreasing. But there wasn't enough rigor in the measurements to be able to say with the confidence you wanted what the trends were doing. And so that's the point at which I, who had been measuring these same things in the ocean, was asked by Ron Prinn, to take over the experimental side of the collaboration. And I just thought that was too important not to say yes, even though it meant the end of all the research I had been doing earlier on oceans and lakes and things of that sort. But I thought this was pretty important.
Describe to me today, then, what the surveillance network is like for this problem.
The nature of the problem is that we're divided by countries, not by individual human beings. And so if you find out that the global trends are not what you expect, then you need to find out why. And that means that you don't want to put your stations in the middle of the ocean because they're not very sensitive to emissions from country A or country B. You actually want to move closer to country A and country B and so forth, all the countries really, and be able to measure downwind when the air comes across an emitter to quantify that emission and identify where it's coming from.
Right. And you can do that from a land or sea-based observational tower? Is that the kind of infrastructure we're building here?
What you want, yes, you can collect air from a tower and run it into an automated instrument, which is the kind of work we do. But you have to be careful about what the location of that tower is. And fortunately, in this global network that's called A-Gauge, which stands for Advanced Global Atmospheric Gases Experiment, we have colleagues in Japan and Korea, South Korea, who have islands where there are stations. And we put some of the instruments at those stations and collaborate with those people. And one of the things about the islands in east of Asia is that they're downwind of China, and practically everything we buy in the stores these days is made in China. And of course, the Chinese economy is growing and Chinese people are doing better than they used to, so they use more things that go into the atmosphere for themselves. So the big story and the big success story is that the Chinese turn out to have emitted CFC-11 in rather massive amounts, about 13,000 tons a year.
This is post the agreement then?
Post the agreement, post 2012, when the production of this compound was totally banned.
But you alerted China to this issue. And,
yeah,
and
it was published. It was published in peer-reviewed literature. The Chinese initial response was, no, there must be wrong, and then they realized it was right. And they did that fairly quickly.
And it could be backtracked to a development that was basically
we
quite
could
a good
basically map it was coming from large population areas of eastern China. They fixed the problem. Those emissions 5 years later had gone, and it wasn't just the ones we could map. It was all of those spurious emissions. So that's a bit circumstantial, but a logical conclusion would be that all of the spurious emissions came from China, and they stopped it. They regulated it. But the good story is that China, having recognized this, is not only shut it down, but they also are building their own monitoring network to make sure it doesn't happen again, because it was tremendously embarrassing. It's an international treaty, signed by 190 some countries. And China's pretty progressive about the environment, with good reason. I mean, the people have to breathe dirty air in a lot of Chinese cities, and I think there's a spirit in China to do something about this.
This is a good news story. I mean, it's often described as the first time that we saved the world. That kind of humanity came together, addressed a common problem. It was a tragedy of the commons. Yes. And we passed good regulations, and we enforce those regulations, and fingers crossed.
Yes.
As long as the nitrous oxide doesn't get out of control, it's getting better.
I think that's true. I think there was a great deal of attention to the ozone holes in the southern hemisphere, particularly in Australia and southern South America and South Africa, because when the ozone hole breaks up in the Antarctic springtime, it drifts northward. And that means that the people who are just ready to go out and go swimming in the ocean because spring has come have to worry about losing their eyesight due to ultraviolet radiation.
I can see how, it was really important that the hole started to affect humans and not just the ice caps. But equally, though, America played a big role, right? It was American chemistry and science.
I think most of the science was centered here, but not all.
No,
a lot of it was in the UK and Europe.
But it wasn't a direct risk to the citizens of North America, right? It could have become so.
Could have been. There are ozone holes that have developed in the Arctic, but they're much less severe. They've been tracked as well. The satellites turn out to be able to measure them quite well.
But what I suppose the point I'm making is that this was an era in which we acted as a human race, as opposed to self-interestedly.
I think that's right.
But here we are facing into an era in which North America feels like it's turning inward. It feels like it's saying, America first, our borders are our borders, we're not interested in anything else. And yet, here we are in an institution that's basically well renowned for its
Yes,
science
yes.
and how it contributes to the global community.
Yes.
And is it at risk of being lost at this point? What's the
short answer is I don't know.
right?
The
Isn't it
political
scary that it's even
situation
in
is
question?
scary, yes, but it's often been scary. I've known Dave Keeling since I became a graduate student here in the 1960s, and he was always worried that his research was considered irrelevant, and it costs money to do things right, and.
But shouldn't we be seeking some kind of endowment then? An endowment for the planet that makes
be wonderful.
That makes this
Yes.
no longer a question of whether if it will survive. It just has to survive, doesn't it?
Yes, and also for people to find the research credible, it has to be supported in a way that's divorced from financial gain. But we need stability too. And one of the reasons we need stability is that young people have to see this as a career option. And if you see something in which every time there's an election, there's a change in emphasis on what we want to do about fossil fuels, or I don't think the ozone layer is quite the same thing because it's kind of a solved problem, but the fossil fuel problem is not solved yet. And, we need some dedication from governments or private foundations or whatever to keep this going, because you cannot make measurements retrospectively. If you haven't made a measurement today, you can't make today's measurement tomorrow.
You need that continuity.
You do.
And I think part of the thing that we need to do as well is just to make sure these stories are understood and known. I mean, I don't mean story by made up. I mean the sort of history of when humanity's acted, who's led, why America is nearly always involved in these endeavours. There's an American spirit which we can't afford to lose when it comes to uniting the world in facing these problems.
I think it actually traces back to World War II. A lot of the greatest scientists who made their careers here in the U.S. Were avoiding the Nazis, and they came to the U.S. and I think the government was fairly enlightened during the war eras, and recognized that government sponsorship of research was something that made sense.
Yeah.
Of course, now it's all at some kind of risk because people are concerned about the amount of money that's being spent. But and they don't appreciate necessarily the long-term reasons for spending that money.
Well, Ray, it's been a pleasure going through this with you and going back to that success story that we should remember and keep talking about and learn lessons from, because we're going to need all of our ingenuity. We're going to need all of the US's creativity and brilliance in science to get us through the climate problem. And we may be having a temporary setback now, but my sense is that this won't stop, that this shift is temporary.
And I thank you for bringing it up and talking about it and putting it on your blog. Let's do another one in a few months when we have a better idea of what's happening.
Okay, well, I'll post about it once we know some news. Thank you so much, Ray, for your time.
Thank you.
Thank you.
Take care.
So that was Ray Weiss, Professor in Geochemistry at UC San Diego. Science moves forward thanks to people like Dave Keeling, Ron Prinn, Paul Krutzman, Sherry Rowland, and Ralph and Ray, all of whom chose to dedicate their lives to academic research and to teaching future generations. They were not motivated by making money or starting the next unicorn business, but they were rewarded with a strong sense of purpose and the knowledge they'd improve the world by furthering our understanding. And perhaps in San Diego, by the opportunity to don a wetsuit and take to the waves as the sun sets into the horizon. My thanks as ever to Oscar Boyd, our producer, our editor, Jamie Oliver, and the growing team who make the Cleaning Up podcast and Leadership Circle possible. We hope you enjoyed this episode. Please join us next week for another episode of Cleaning Up.
Cleaning Up is brought to you by the members of our Leadership Circle. That's Actis, Alcazar Energy, Davidson Kempner, Ecopragma Capital, EDP of Portugal, Euroelectric, the Gilardini Foundation, KKR, National Grid, Octopus Energy, Quadrature Climate Foundation, STCL, and Wärtsilä. For more information on the Leadership Circle, please visit cleaningup.live. That's cleaningup.live. If you're enjoying Cleaning Up, please make sure that you subscribe on YouTube or your favorite podcast platform and leave us a review. That really helps other people to find us. Please recommend Cleaning Up to your friends and colleagues and sign up for our free newsletter at cleaninguppod.substack.com. That's cleaninguppod.substack.com.